Hello and welcome back everyone to the second section of the YOLO series. In this section, we're going to be talking about the different versions of YOLO, starting from its inception up until this point. And in this video, we're going to delve into the YOLO version 1, which is the most accurate and fastest object detector in 2016. The topics that are going to be covered in this video, on the first section, we're going to talk about the introduction to YOLOv1. On the second section, we're going to talk about the algorithm in detail. On the third section, we're going to look at the architecture. And finally, we're going to conclude by talking about the loss function in order to evaluate the model. Now, let's start by introducing YOLOv1. You only look once broke onto the computer vision seen in 2015 via a paper written by Joseph Redman, Santosh Diwala, Ross Gershik, and Ali Farhadi. And the object detection evolved from the traditional methods to the deep learning methods, moving from YOLO-Jones detectors, HOG detectors, and deformable parts models to the most recent convolutional neural networks and deep convolutional networks. So before we go directly into YOLOv1, let's see the evolution of object detectors. So the first object detector was the YOLO-Jones detector. It was the first one which did a facial recognition and gave extremely good results. So for example, when you use your camera on your phone, you can directly see tiny boxes identifying the faces of people in that image. So that's basically using a YOLO-Jones detector, and it used a sliding window which searched across the image to find a bounding box in which the face is enclosed. And that's all you need to know about the YOLO-Jones detector at this time. It's very good at identifying faces. And the second one was the histogram of oriented gradients, and it was invented in 2005, and it was very good at identifying people in an image. So, for example, if you have pedestrians walking on the road or on the street, you can identify them by using HOG. And HOG detector came, which used gradients that are computed to find the ages of objects. And finally, after these gradients are collected, then we create a histogram for those gradients. And it was scale invariant, and it can detect objects at different scales. Recently, CNNs are the state-of-the-art models that are being used to detect objects. And around 2012 was the time when deep learning had won the ImageNet challenge, which is AlexNet, and the world saw the rebirth of convolutional neural networks. After 2014, object detection took a two-phased approach. The first one is one-stage detection, which includes today's topic, YOLO, and other single-stage detectors such as RetinaNet and single-shot multi-box detector. And the second one is a two-stage detection, which contains all of the RCNN families, and we will look at them briefly. So the RCNN was released in 2014, and as you can see from its name, it has an R, and it stands for regions, because it's based on regions that are proposed from an image. So for example, if you have an image containing a person riding a horse, and if you want to locate this object, the person and the horse, you need to find regions corresponding to the person and the horse. So how do you find these regions? So in order to find the candidates or the regions of interest, which in short is called an ROI, we need to the RCNN model just used a handcrafted feature extraction method, such as selective search, and you can use a sliding window approach, and then by using after these regions are proposed by using that method, then you resize the image so that it could be equal to the input size of the CNN classifier that you're using. For example, if you use VGG16, you need to warp the image so that it's going to fit inside the model at the input of the model. And then finally, you just predict the class, and you also predict the position of the object. The second one was FastRCNN, and it was released in 2015. It is an improved version of the initial RCNN, but most of the upgrades concern the speed. And the region proposal was the same as RCNN. So, for example, it uses selective search or other methods. But what made it different was instead of just computing those regions directly from the image, first you use a convnet to extract features from the image and create a feature map, and you project and extract those regions. Those region proposals are made on the feature map instead of the image. Then finally, you use an ROI pooling layer in order to select some attributes or features from the feature map, and then you train a bounding box regressor and a classifier. Next was the FastRCNN, and the FastRCNN was the most robust version of the RCNN family. And initially, we saw that the region proposal stage was just selective search or some type of handcrafted algorithm. And what kind of adjustment was made in the FastRCNN was that instead of using a handcrafted feature extraction method or region proposal method, they used convolutional neural networks to propose those regions. So first, we need a convolutional neural network to extract a feature map, and we use another convolutional neural network to propose the regions. And by using the originally computed feature map and the proposed regions, finally we can train a classifier and a bounding box regressor. So accurate object detection is very slow. So for example, when you compare YOLO with the RCNN family, the RCNN family is more accurate compared to YOLO, and YOLO is much faster than the RCNN family. So if you want higher accuracy, you need to compromise on the speed. YOLO has a speed of 45 frames per second, and FastRCNN has a speed of 7 frames per second. So it's very slow. But when you compare the mean average precision, FastRCNN is much higher than YOLO during the initial stage. Now let's take a look at the algorithm in detail. YOLO combines what was once a multi-step process using a single neural network to perform both classification and prediction of bounding boxes for detected objects. So the multi-step process, which was used by the RCNN family, was changed into a single neural network, and YOLO just looks at an image once and only once, hence the name You Only Look Once, which allows it to capture the context of the detected objects. So what are the advantages of using YOLOv1? First, it's very fast. As I mentioned before, it runs in real time at 45 frames per second, which is much faster than the RCNN family. Second, it gives less errors, less than half of the number of background errors compared to FastRCNN. Third, it generalizes well to the representation of various objects, making it more applicable to a variety of new environments. The fourth one is it provides less false positives. It halves the number of false positive predictions. In the videos that I made about IOU and maximum suppression, we talked about false positives. And these false positives are predictions that don't have that much IOU overlap. So we have the true positives and false positives, and the sum of the two will be the total number of predictions outputted by our model. But ideally, we want just one predicted bounding box enclosing our object. So we need to reduce the number of false positives so that we don't have a redundant number of bounding boxes. So that's reduced in YOLOv1. So let's delve into the algorithm in detail. So first, if we're given an image, which is so the image input size might be 480 by 480, and we divide it into an S by S grid where S equals to 7. So we divide it into equally sized grid. Second, we represent each cell, and each cell is going to predict 2 bounding boxes. So in YOLO version 1, only 2 bounding boxes can be used per cell, and we're going to use confidence score for those boxes. These confidence scores reflect how confident the model is that the box contains an object, and it's given as the probability that the object is located inside of the box. Once we have the bounding box, the 2 bounding boxes per cell, and the probability of an object, then we have to define the class probability. Each grid cell also predicts conditional class probabilities. So on the original Pascal VOC dataset, which was used to train the YOLOv1 model, we have 20 different classes, and each cell would predict the class for the object. So for example, we used different color encoding in this image. The car is predicted by using an orange color, and some of the cells are colored in purple, which show the bicycle, and some of the cells predicted dog, and some of the cells in cyan predicted dining table. So each cell must output a class probability, and it's a conditional probability of the class given that there is an object. Then we combine the 2 boxes which are predicted by every cell, and the class predictions are given by different colors. Then we have this image. So each predicted bounding box, depending on which class it's predicting, is going to be given a different color. Next, we're going to look at how to identify the position of the object. And in order to identify the location, we need to know the center coordinate. The cell in which the center of an object, for instance, the center of the dog resides, is the cell responsible for detecting that object. So as we can see from the image, the center of the dog is contained within the cell that's shown in light green, and that cell is going to be responsible for predicting that object. So in YOLOv1, each cell is responsible for predicting only a single object. We need to pay attention to this point. And a bounding box prediction consists of 5 elements. The X, Y, W, H values of the bounding box and P object. So these are the coordinate values, X, Y, W, and H, and P object is just the confidence score, the probability that there is an object whose center falls within the grid cell. So we have 5 elements. The X and Y coordinates of the bounding box are predicted relative to the grid cell and not the entire image. So the X and Y coordinates for the center point of the object that's contained inside the light green grid cell are going to be predicted relative to that grid cell and not the entire image. But the width and height are predicted relative to the entire image. For use later in loss calculations, the ground truth bounding box coordinates are all parameterized to be between 0 and 1. The width and the height of the bounding box are calculated as the ratio of the entire image's width and height. We need to divide the width and height of the bounding box by the width and height of the image. And the XY grid cell offsets are parameterized as the ratio of the grid's width and height. So let's take a look at an example. So if you're given an image which is 448 by 448, and we divide that image into a grid cell that is 7 by 7, by dividing the width and height of the image by S, which is 7, we have a grid dimension where each grid cell is going to be 64 by 64 pixels wide. Therefore, a bounding box from our dataset that has X and Y coordinates given as 32 and 16 respectively, and a width and height of 300 and 150 respectively, would be parameterized as 32 and 16. We divide them by 64, which is going to be the dimension of our grid cell. And we computed this 64 by dividing the width and height of the image by 7. Then we get 64. Then we divide the X and Y coordinates by 64, because as we mentioned before, it has to be predicted with respect to the grid cell and not the entire image. And the width and height also need to be between 0 and 1, so we divide by the dimensions of the entire image, and we divide it by 448. So if you look at the annotation for the Pascal VOC dataset, it uses the top left and the top bottom right corners of the image instead of the center coordinate for the image. So we need to convert this kind of annotation into the center coordinate if we want to train our model. So a sample image with its corresponding annotation file is shown below. The parts of the annotation file to observe have been highlighted in red. In this case, we need to convert the min-max encoding to the center encoding first. Let the bounding box coordinates in the min-max encoding be defined as b min-max, and the bounding box coordinates in center encoding be defined as b center, and let uppercase W and H are the width and height of the entire image respectively. And converting from b min-max to b center can be simply defined as if b min-max is given as x min, y min, x max, and y max, then in order to compute b center, we add the x coordinates, which is x min and x max, and divide it by 2. Then we multiply it by the width of the entire image. And we also do the same for the y coordinates. So we add y min and y max divided by 2 and multiply by the inverse of the height. And we take the difference between the two x coordinates, x max and x min, so that we can find the width of the bounding box. And we take the difference between y max and y min in order to find the height of the bounding box. So we currently computed B center, which contains the XY location of the object center, and the width and height of the object is scaled between 0 and 1, but our job is not completed yet. To convert this to YOLO bounding box encoding, BYOLO, which takes the X and Y location of the object center relative to the image's width and height, and converts it into XY coordinate relative to the grid cell. So now the one that we computed is just relative to the entire image, and we need to convert it into so that it becomes relative to the grid cell. The width and height are left as they are in the YOLO encoding. So we don't do anything to the width and height computed before. So in this formula, we have X, C, Y, C, W, and H on B center in order to compute B YOLO. first we multiply xc and yc by 7. And why did we multiply by 7? Because previously when we computed xc and yc, we divided by the width and height when we computed in the B-center. And when we multiplied by 7, what we're doing is, according to the previous example we did, we divided the x and y coordinates by 64, which is the dimension of the grid cell. So in order to get that 64, we need to multiply 7 by the width and the height. So when you cancel out by 7, it becomes 64. So that's why we multiply by 7. Then we subtract the offsets from the top left corner of the image. So the grid cell is located at a position that's further away from the top left corner of the entire image. And this can be represented by using offsets in the x direction and in the y direction. And these are given as gx and gy. And we subtract these values from the center coordinates xc and yc, so that the offset from the entire image is balanced and removed, and we're just computing relative to that particular cell, and the width and height will stay the same. So the output for our YOLO model for a 7x7 grid, for the ground truths label, we're going to have a class prediction given as C, X, Y, W, and H, the 4 coordinates representing the center of the object, and the width and the height of the ground truth bounding box. And then we're going to have the class predictions and the confidence score in addition to the 4 coordinates. So the probabilities of the cat, given that it's an object, for the 20 classes, we're going to have 20 different predictions. And the confidence score just tells us whether there is an object within the box. So in total, if we have a 7x7 grid, and then we have 25 points to represent, 4 for the coordinates, 1 for the confidence score, and 20 for the class predictions. In total, we have 7x7 by 25 ground truths. And for the prediction bounding box, we're going to have 2 bounding boxes per cell. Remember at the beginning of the video, we said that we used 2 bounding boxes per cell. So each bounding box are going to have their own center coordinates and width and height. And for the first one, we're going to use C1 as a confidence score. X1, Y1, W1, and H1 will be the coordinates for the first bounding box. And we do the same for the second bounding box. And the class predictions will stay the same, which are going to be 20. So in total, for the prediction of bounding boxes, we're going to predict 7x7. Then we have 2 bounding boxes. Each of them have 5 coordinates plus 20 class predictions. So in total, we have 7x7 by 30 tensor. And it's shown by the image, which is represented by 3-dimensional structure. And in total, we're going to have 1,470 predictions. Now let's take a look at the architecture or the feature extractor for YOLOv1. The initial convolutional layers of the network extract feature from the image, while the fully connected layers predict the output probabilities and coordinates. So the convolutional layers are responsible only for feature extraction process, and the fully connected layers predict the output probabilities and coordinates that we mentioned before. So the YOLOv1 architecture has 24 convolutional layers and 2 fully connected layers. And alternating 1x1 convolutional layers were used in order to reduce the feature space from preceding layers. 1x1 convolutional layers are used in order to reduce the number of channels, which is the depth of each layer. And we're going to look at the image so that we understand the concept. So initially, we're going to have an image that's 448 by 448. And the first conv layer is going to be by 7x7 by 64. and a stride of 2 will be performed. And whenever you perform a stride of 2, you're going to reduce the dimension by half. And another max pooling layer with stride of 2 is going to reduce the dimension by half again. And the next layer will have a dimension of 112. We also perform a conv layer and max pool layer. And the max pool layer has a stride of 2, so the dimension will be halved again. And we perform a bunch of 1x1 and 3x3 convolutions, and finally a max pool layer, which reduces the spatial dimension. And we mentioned that 1x1 convolution reduces the depth of the network. So the depth, if it was, then it allows us to change the depth. And on the next stage, we perform the 1x1 and 3x3 convolutions again. Finally, a max pooling layer, and then we do a bunch of convolutions again until we reach a fully connected layer, which is 4096, and then we reshape that into 7x7x30, which is the output layer that we have seen previously. Finally, we're going to talk about the loss function that's used in YOLOv1. If you look at the original formula for the loss function of YOLOv1, you think it's going to be very messy and very complicated, but actually it's not that hard, and it can be broken down into pieces so that you can understand what each piece is doing. So there are 5 terms in the loss function. So a loss function is basically a function which tells us how much our prediction is deviating from the ground truth label. So if you have a true label of an image for a cat, how confident is the model? And we compare the prediction from the model from the ground truth label. And we do the same for the predictions of the bounding boxes. So the first term of the loss, it's going to minimize the loss for using the sum squared error of the x-y coordinates. So these x and y coordinates predictions might deviate from the true labels of x and y of the bounding box, and we're going to try to minimize the loss for the xy coordinates. And they're also bounded between 0 and 1. And you see that there is a term, there is a function which shows 1 obj ij, and this basically is an identity function which is going to be 1 when there is an object inside the box, and which is going to be 0 when there is no object. So if it's not an object, it's not worth calculating the loss in the first place. So we just give a value of 0 and cancel this term. And the second term, the bounding box of the width and the height are normalized by the image's width and height so that they fall between 0 and 1. And we're going to minimize the loss for the predictions of the width and height from the labels that are given to the true bounding box or the ground truth bounding box. And here on the xy coordinates, we didn't use a square root, but here we're going to introduce a square root. Since small deviations in large boxes matter less than small boxes, square root of the bounding box of the width and height are used instead of the width and height directly to partially address this problem. Because for larger boxes, when you take the difference, it's going to be much larger, and when you square that difference, it's going to be a very large loss. So when you put them under the square root, is going to minimize that deviation. So the second loss is just responsible for minimizing the loss for the width and the height. For the third and the fourth term are just for the confidence score, the C terms that we mentioned before. And in every image, many grid cells do not contain any object. So they don't contain an object. So if there is no object, for the first term, we used obj, and for the second one we used no obj for the identity function. So if there is no object, it's going to be 1, and when it's for no obj, when there is no object, the identity function returns 1, and when there is an object, it's going to return 0, which is the inverse for the identity function 1 obj. And this pushes the confidence score of those cells towards 0, often overpowering the gradient from cells that do contain objects, and makes the model unstable. So the loss from confidence predictions for boxes that don't contain objects is decreased by using a lambda parameter. So we also introduced a lambda parameter, a lambda no obj, which is going to be 0.5. And this value are just picked by the authors, and they're just going to maximize or minimize that loss. So if you think that no obj is very, very important, you give a high lambda value. If you don't think it's important, you give a very low value, which in this case is 0.5. And we also used lambda terms for the x, y, and wh parameters. And we want the loss from the x and y coordinates to be weighted higher. So we're going to use a very large lambda value, lambda chord. And that value, I think for the YOLOv1 paper was 5. And the fifth term and the final term is going to be the sum squared error of the class probabilities, so the class predictions that are outputted by the model. And the lambda chord, due to the same reason mentioned in the third and fourth terms, the lambda chord, the coordinate that I mentioned before, we need to increase the loss from the bounding box coordinate predictions, so the lambda chord must be a higher value. And we need to minimize the lambda parameter for the no object because those are not that important. So last time we talked about min-maximum suppression. So since YOLOv1 uses a 7x7 grid, then if an object occupies more than one grid, so you might have a scenario in which one object might be very large and it's not going to be contained within that grid cell, so it's going to be detected by multiple grid cells, and the object may have a lot of predicted bounding boxes. And since we need any object to be detected only once, for example, the taxi in this image may be detected 3 times by 3 consecutive cells, which is 3, 0, 3, 1, and 3, 2, where the red box is a ground truth box. So since each grid cell predicts only 2 boxes, because I told you that each cell is just responsible for predicting one object in 2 boxes and can only have one class, this limits the number of nearby objects that YOLO can predict, especially for small objects that appear in groups such as flocks of birds. So for example, let's say even those taxis on the back that are overlapping, or when you see a bunch of people taking an image very close to each other, if you don't use a very fine grid, that's more than 7x7, since each grid cell is responsible for predicting one object, it's going to miss some of the objects because those are not going to be detected. And YOLO can detect only 49 objects, and it has a relatively high localization error. So that's all about YOLOv1, and in the next video, we're going to look at YOLOv2.